Ever wonder what the hidden engine is behind all the AI that's changing our world? You know, the stuff that recommends your movies, understands your voice, and is learning to drive your car. Well, it's not just a bunch of code. It's a very specific branch of mathematics, and today we are going to pull back the curtain and explain it.
So, let's kick things off with a question. Just think about all the AI you interact with, maybe without even realizing it. Netflix, guessing what you want to watch next. Your phone, understanding what you say. Or even those super complex systems that are going to navigate our cars someday. What is the one common thread that ties all of that amazing technology together?
The answer, and yeah, this might be a little surprising, is a field of math that a lot of us probably haven't thought about since high school. It's linear algebra. But today, it's become the fundamental language that AI uses to see, hear, and make sense of the world.
So here's the plan for this explainer. We're going to start with the absolute basics, the data structures, then move on to some of the key operations, and we'll wrap up by solving a really common coding problem that, trust me, every single AI developer runs into.
Okay, let's get right into our first section. Before we can do any of the cool, complex math, we need the right tool for the job. And in the world of Python and data science, that tool is, without a doubt, the NumPy array.
So think of it like this. A regular Python list is kind of like a grocery bag. You can toss anything in, but all the items are stored in different places in memory. A NumPy array, on the other hand, is like an egg carton. It's this tightly packed, super organized grid. And that structure lets a computer process data hundreds, sometimes thousands of times faster. For AI, which is all about crunching huge amounts of data, that kind of speed isn't just a nice-to-have, it's absolutely crucial.
And that brings us to the core concept here, this thing called an ND array, or n-dimensional array. This is what gives us the superpower of vectorization. It means we can perform math operations on entire arrays of data all at once, instead of having to write these slow, clunky loops in Python. It's a total game changer.
Now, this image shows something you really need to get locked in your brain. In the NumPy world, we don't really talk about rows and columns. We talk about axes. So axis 0 is the rows, and axis 1 is the columns. It might seem like we're just swapping words, but believe me, thinking in terms of axes is the key to understanding and manipulating data shapes correctly.
All right, so we've got our data structure down. Now let's look at one of the most fundamental operations, multiplication. And right away, we're going to hit a point of confusion that trips up almost everyone when they're starting out. Let's untangle it. Seriously, if you've ever worked with NumPy, you have asked this question. You've got these two functions, dot and inner, and for simple little vectors, they give you the exact same answer. So why do we need both? Well, the difference between them actually reveals something really deep about how these operations work in higher dimensions. So first, let's cover the simple case. If you're just working with one-dimensional arrays, vectors, then dot and inner are completely interchangeable. They do the exact same thing. They perform the classic inner product. You multiply the corresponding elements, and then you sum them up. No difference whatsoever.
But look what happens the second we move up to 2D arrays or matrices. Whoa, the results are totally different. np.dot is doing what we call standard matrix multiplication. We'll get to that in a second. But np.inner, it's doing something else. It's almost like it's treating each row of the matrices as its own little vector and then calculating their inner products. It's a really subtle but incredibly important difference.
So how are you supposed to remember this? Well, thankfully, some smart contributor on Stack Overflow gave us the perfect little rule of thumb. For 2D arrays, np.a, b is exactly the same as np.inner, a, b.t. In other words, the dot product is really just an inner product where you flip or transpose the second matrix. That right there is the key to unlocking the whole thing.
Okay, now that we've cleared up the whole dot versus inner thing, let's really zoom in on the rules for standard matrix multiplication, because honestly, getting this right is non-negotiable for building any kind of neural network.
This right here is the golden rule. It's everything. For you to multiply two matrices, their inner dimensions have to match. That means the number of columns in the first matrix must be equal to the number of rows in the second. If they match, the resulting matrix gets its shape from the outer dimensions. And here's a perfect picture of that rule in action. We've got a 2x3 matrix and a 3x1 vector. See how the inner dimensions, 3 and 3, match up. That means the operation is legal. And the result? It gets its shape from the outer dimensions, giving us a 2x1 vector.
It's the exact same logic when you're multiplying two full matrices. Here we have a 2x3 times a 3x2. Again, the inner dimensions, the two 3's, They align perfectly. You can almost think of them as canceling each other out, leaving us with a 2x2 result from the outside dimensions.
So what happens when your dimensions don't align? Well, one of your best friends is the transpose. All you have to do is call .t on a NumPy array, and it just flips it along its main diagonal, swapping the rows and columns. It's such a fundamental trick for getting your data shapes to play nicely together.
And one last thing before we get to our practical example, the identity matrix. It's super simple. You know how multiplying any number by 1 just leaves it unchanged? The identity matrix does the exact same thing for matrix multiplication. It's the neutral element, and it's surprisingly useful.
Okay, so why do we care so much about all this theory, all this talk about shapes and dimensions and axes? Because when you're in the trenches, writing code, things are going to break, and understanding these rules is what allows you to fix them. So let's walk through a classic real-world error.
So picture this. You're working on a model. You have 2 arrays you need to multiply. The first one, y2, is a column vector with a shape of 50 by 1. The second one, lambda_0, is a slice you took from another array, and its shape is just 2.
So you go to multiply them with np. You hit run, and bam, you get this famous or maybe infamous error, value error. Matrices are not aligned. I swear, this is a rite of passage for anyone starting with NumPy or machine learning. It's so frustrating.
Okay, so we know the golden rule, right? The inner dimensions have to match. Here, they're 1 and 2. So that's why we got the error. But the deeper, more important question to ask is why? Why is the shape of our second array 2, which is a 1D array, and not 1, 2, which would be a proper 2D row vector?
And here it is, the problem and the solution, side by side. When you slice a 2D array using just a single number, NumPy tries to be helpful by simplifying the result into a 1D array, which means it drops a dimension. The fix is to be explicit. You have to tell NumPy exactly what you want. You use the reshape method to force that 1D array back into a 2D shape. And just like that, our shapes become 50, 1 and 1, 2. The inner dimensions, 1 and 1, now match perfectly, and the code works.
You see, that little debugging exercise shows us that understanding linear algebra isn't just some abstract academic thing. It's the practical, hands-on skill you need to build and, more importantly, fix the AI systems that are literally reshaping our world. It's the language of data, a language of shapes and transformations. So I guess the only question left is, what are you going to build with it?